Thank you for the introduction. My name is Juan Cruz, and I'll be presenting our work here. So in recent years, there's been a growing trend for these offsite construction. So in our research project, we're particularly looking at precast components that are manufactured offsite and then brought onsite to complete a structure construction. Typically on the offsite construction of these, the inspections and quality inspections and things of the sort is very thorough on the offsite. However, when you get on site, it becomes much more difficult because of a different operating environment and different access to sensor and sensing equipment. So typically, the manual on-site inspections tend to be more labor-intensive, time-consuming, and prone to human errors. So we saw opportunity there for automated inspection that is bringing in research, robotics research into the space to perform higher quality inspection on site. And there's been a lot of background and related work to this. So drones have become very popular in both industry and research for this type of application in both structural and health monitoring for these and surveillance of construction sites. There's been a lot of work in ground robots as well. They offer good flexibility in terms of operating times and being able to have, carry heavier payloads. So we saw a lot of opportunity there for multi-robot inspection that is combining the approaches of both drone aerial robots and ground robots to have more flexible operating conditions to perform on-site inspections. Now, ideally, we'd like this to be fully autonomous, but the technology is not really there yet. There's still a lot of complications when you're working on different construction environments. So because of that, most frameworks have a human in the loop condition. That is, a human at some point in the framework providing control and direction to the robots. That can be done through different teleoperation methods and different control interfaces. Now, for this particular application, we're looking at gaze-based robot control because we've seen a lot of potential there for intuitive control methods. And then the final point is more related to research in general, and that is software replicability. In general, most research starts from the ground up in terms of software. So we want to provide some frameworks there and see what it could be applied to make that more user-friendly. So as I described, we're using an aerial robot and a ground robot in order to facilitate an on-site inspection. So we have a human operator. In this case, the human operator is using the eye tracking capabilities to provide contextual data to the ground robot. So that is using their gaze and fixation points at certain points within the inspection pipeline in order to give additional information as to what exactly needs to be inspected in terms of the components. This is facilitated through different interfaces. So for the drone, we have aerial controllers that the operator would use. And then we also have a application user interface that we developed for the data streaming through the ground robot and coordination between the two. And it's also open source. So at the end of the slides and in the paper, we provide links to that. This is a block diagram of system design. So as I said, we have ground robots. There could potentially be a fleet of ground robots or a drone. What we have though is going back to the previous slide. So when we go to the drone capabilities, we initially want to get some waypoints. So we want to know where the object to be inspected is in the construction site, because our initial map might not match the current state because things tend to get moved around and things of the sort. So we want to create waypoints, GPS-based waypoints that construct a mission that is multiple waypoints. And with the drone, we also want to get some contextual information so the ground robot can then do the autonomous navigation to the location. And that contextual information in our case is a target reference images. So that is images of the object to be inspected so the ground robot has some context to later do through a computer vision pipeline or things of that sort. So as you can see here, it's streamlined, centralized through a user interface app where the operator can coordinate the data flow. You have the gaze module, as I discussed. And we have an additional module there at the bottom. This is a segmentation module. So with the gaze-based data, we get pixel coordinated points. So very fine, low-level information. And we want to expand that and add to that in order to get a larger grained information of what needs to be inspected. So with a single point, say a girder, you can get a larger mask of what the robot should be inspecting. And this, as an addition to the system design, we use a containerized architecture. So containers such as Docker containers, where we use in this work, can be coordinated through a Docker compose, which allows you to coordinate multiple containers into a larger application. So containers are typically isolated. That is, they're isolated virtual environments or virtual machines, but are much lower level. So they have kernel level access and are ideally, they can be replicated on any computer. So through a configuration file, you can spin up this environment and have a whole application deployable very quickly. So we manage the communication and data flow between these different isolated environments using the 0MQ data library and proxies between them. And this is an image of the user interface, for the ground robot and aerial streaming. So one of the benefits of this is we use a browser-based application. So that allows us to deploy on multiple operating systems and multiple browser types. As you can see here, we have buttons for the state indicators for where the robot is within the mission pipeline, which we'll see in the next slide. And we also have some April tags. So as we've said, the operator has gaze interface. So these April tags allow us to create a bounded area in which the gaze is used. So that allows us to get a very precise pixel level location of where the user is looking and where they're fixating on. So we tested this software as we tested in an outdoor environment. We have a drone cage of the UTSA that allows us free range and free roaming within this space. So we tested with a mock environment. You see a bridge there we put in for the environment using a local Wi-Fi network where we had a human operator coordinating these two robots with the application. We used DJI Matrix drone and the A200 ClearPath ground robot, and then the pupil core eye tracking glasses. So let's see. Oops. Yeah, so at a high level, the mission workflow would look like this. We have 3 stages. The data gathering stage, as I said, this one is where the human operator would send a drone to a location. So if you were going to inspect that bridge from the previous picture, you would send the drone there first, gather GPS-based waypoints, and then contextual images. And then if you have multiple, you could get multiple of those. Once you have those, you then save those and you pass those to our user interface. Those then get sent to the mission execution phase, in which the ground robot or fleet of ground robots would coordinate to dispatch to those locations. Once they autonomously drive to those locations and find the area of interest, then you would have the inspection phase, and this is where the gaze-based portion comes in order to get more fine-tuned data and also specify what exactly you want to inspect within this construction component. And as you can see here, this is the deployment phase of it. So the orange area there is the segmentation mask that we create. The red point, if you can see it, is the fixation point. So once the user fixates on a target, we then segment that area, and the ground robot would then know to intelligently navigate to that area and perform a surface level inspection or whatever kind of inspection would be needed. The next slide. Yeah, so that concludes my presentation. Just to go over the key contributions, we developed this novel containerized multi-robot architecture. It had gaze tracking integration through a platform agnostic interface. We completely open source the design, so it's there if anyone wants to build off of it or replicate it. Some limitations, so we only implemented up to the inspection phase, so the actual inspection portion we didn't complete, but that may be planned for later work. The GPS navigation we found to be sort of limited, especially in this kind of, even in an open area, with our GPS sensing hardware, we could only get sub-meter precision. So that made some of the autonomous navigation difficult. The potential image relevancy degradation. So if you take an image, say like a few hours with the drone prior, then sending the ground robot later could limit your contextual navigation capabilities. Future work, we would like to extend this to more usability studies and actually applying it to larger realistic scenarios. And we'd like to acknowledge our funding for this work for the Trans-IBIC and NSF. And then all the citations in this slide match those of the paper. And that's it.